Hi, here's another devlog video about my train game Steam Revolution. I wanted to make a relatively quick update video that talks about how I've done some optimization to make the game run faster. This time, specifically, my focus has been to make the simulation run faster. Previously, I had done some sort of optimizations to make the smaller, just level maps run quickly enough, but before doing any major down deep optimization, I wanted to make sure that I actually had a level that was big enough where it needed it. And so in particular, that's the large world map and trying to connect all the different cities and indices inside of that. Until this point, I'd done all of my testing on small maps and just didn't have the need for something to run any faster. However, once I got my world map filled out to a large degree, the amount of time it was taking to actually run the entire simulation from start to finish to where it would unlock a new city was taking on the order of about an hour, and that was just unacceptably long. And one of the things I knew from the outset was going to become a problem, and then I confirmed was a problem, is that I had a particularly inefficient piece of code in the simulation where I was trying to determine what platforms a train could load or unload from. Basically, I was doing something that was kind of silly, which is for every train car, I was looping through the entire list of all the possible platforms and determining, is this platform close enough or not to be loaded from. The obvious solution for how to do one of these spatial lookups faster is to use some sort of a spatial partition lookup structure, and it just so happens to be that I already had something to do that, which I'm using in the track editing. When you place a track, it has to determine which of the trees are too close to the track and need to be cleared. So I adapted the code for that, made it more general, and added all of the platforms, and then I could more quickly query what platforms are close to one of the train cars. And this gave a pretty good speed up of about 3 times faster overall for the simulation. At this point, I should maybe talk about how I was actually measuring the amount of time spent. It was going to be way too slow to actually run the map to completion, so I did a test where I start the simulation and ran 100,000 simulation ticks and just measured how long that took. Perhaps fairly and perhaps not, I included the loading and the simulation initialization time in this instead of just the actual simulation tick calculation time. At the time, I thought that was probably fair because it was a little bit annoying to have to wait a couple of seconds when I hit start simulation for all of the loading and validation to happen. In retrospect, I wish I had done a better job of splitting those out because they sort of cross-contaminate and it's hard to tell exactly what fraction is what now in looking back at my timing notes. If I recall correctly, I was most annoyed by this initialization time at the beginning, and I also saw some opportunities for the initialization to use the same tree lookup acceleration structure, and so I did that first. So I think that that is included in my initial 3x speedup. Once I had implemented that, however, I realized that I could do better. And in particular, instead of doing any sort of a spatial lookup at all, I could store the path to the industries on the tracks themselves. And the tracks themselves basically are split into segments, and then it's like, okay, well, the segment that the train is actually on is the space that you care about. This was way more efficient and just about doubled the speed again. The problem was that my data structures were a little bit awkward. That I was storing the paths inside of like the platform data structure instead of the track data structure. And so a bit of reorganization needed to happen in order to make it work. The details aren't super interesting, but yeah, I did that. At this point, to have the sampling profiler be a little bit easier to read the results from, I decided it would be better to split my simulation function into multiple sub-functions so that I could know how long each one of those sub-functions was taking. I wouldn't have expected this to have any change at all in terms of how the program ran or what the timings were, but for some reason it ran a little bit faster, and I can only guess that maybe the optimizer wasn't able to handle a large function. It really kind of baffles me. At this point, I saw that there was a fair bit of time spent calculating the attributes of the track at different locations, like what is the position, what is the slope, and things like that. So I made that code a bit faster. At this point, my focus then became to make the collision detection between trains a bit faster. One of the most obvious things to do was that the trains were having 3 different bounding spheres that were being tested, and I reduced that to 2. That didn't really help too much. The main reason that this didn't help as much as you might think is because I was already doing a coarse-grained culling, and this sphere inter-train collision was only done as the fine-grained collision detection. However, a lot of time was being spent in the coarse-grained collision detection, and that's when I was calculating a bounding box for the train itself from the train cars. The coarse-grained collision detection doesn't need to be super accurate, and in general, if you look at the map, it's mostly 2D with a small amount of 3D, and so by reducing the dimensionality of the bounding boxes, that actually gave a pretty decent speed up. Turning our attention back then to when the cars are loading and unloading cargo, what was happening originally was that every simulation tick, when it was trying to determine if it could load or unload, it was looking up what are the nearby paths and calculating, okay, I should be loading or unloading based on states. I modified this so that instead, when the train first arrives at a station, it calculates all of the states and what it should be loading and unloading to, and caches that. And that makes then all of the subsequent updates much faster. I then found that a surprisingly large amount of time was spent doing a pushback unique function call when claiming blocks of track for a train, and this wasn't actually necessary. It was possible to just do pushback. I was a bit surprised because pushback unique is looking through the array and checking all of the entries to determine if it should add or not. But the length of the arrays of train IDs should generally be quite short, so I was expecting this wouldn't actually matter in terms of performance, but I guess it did. I then noticed that when trains are leaving from the depots, before a train is able to leave, it needs to have an empty block that can move into. And the amount of time spent checking whether the block was empty or not was a little bit high because it had to do some indirections and look up some values. So I modified that so that the depot itself would cache what the block ID was, and that made a pretty sizable impact. To show that we're getting into the realm of micro-optimizations here, I discovered that calling resize 0 in my custom little vector class was actually slower than clear by a fairly significant margin. And that's because the resize was making a function call that's like checking, hey, is the capacity high enough already for the new size? And if not, then expand it. I would have thought that this would be pretty fast and just negligible in terms of execution time, but it turns out that it actually was costing something. I think I had originally written this because my clear was freeing the memory, and then at a later date I decided that clear should just set the size to be equal 0 and leave the memory allocated the same way that the standard vector does, and I had just never changed the code that was calling it. I'm actually not sure in my notes I was referring to when I said I remove redundant lookups in update cached car data, but this other change is also related. Basically, the cached car data are the track attributes, and when I'm looking up a track is composed of lots of little micro segments. Each segment has a stored slope and curvature. Importantly, the length of the segments is not constant. This means that given a parameter of how far along the track one of the cars is, I need to determine which of the segments actually is storing that information. If I don't have any prior knowledge, then I make an estimate and then adjust based on the result of whether I'm ahead of or behind the segment, because each segment stores a range of beginning to ending distance. But a lot of the updates to a car position are going to be a small incremental movement from a previous location. And in that case, I can store which segment index the car was previously on, and that should be a really good guess of what one is going to be in the next time. And so that sped things up. In a somewhat similar vein of using the previous train location to inform the new location, if the train didn't move at all, then that means that its bounding box didn't change and I don't need to recalculate it. I hadn't mentioned this yet, but the way that I'm accelerating the collision lookups between trains is that I have a regular grid of collision tiles, and I store references in those of what trains are inside of the tiles. The way that I was originally dealing with this was at the beginning of the collision update, I would clear all of the tile information so that none of the tiles had any train references. Then I would loop through all of the trains and calculate their bounding boxes, then add references of the trains to the tiles. Then when I'm doing the collision, I could quickly look up what trains are close by. As it turns out, just touching the data to set the tile references to be empty was taking a lot of time. And so I modified this to iteratively update the train references in the tiles. In other words, if nothing changed about what tiles the train was in, it would just leave it alone. If the train did change something, then it would clear out the tiles just of that train ID and then add the train ID to the tiles that the train now occupied. This also allows a nice little optimization that if a train speed is 0, then all of this can be skipped for the train. And the speed of a train being 0 is actually reasonably common because a fair number of trains are going to be either waiting at junctions for other trains to move, or they'll be waiting at a train station to load and unload cargo. So far my optimizations have mostly been about the trains, but there's also industries, and they need to do stuff like consume resources and generate products. And some of the logic for that was a little slower than it really needed to be, because I was having to keep track of the control flow using like a Boolean of, hey, did I find a product that can be generated? And if so, then, do something. Instead, I modified that to directly use goto statements to jump to the necessary code, and that made things faster. Additionally, to determine if a region could be unlocked, it's necessary to check whether the capital cities have gotten the amount of resources that they need. And just looping over all of the industries instead of all of the capitals was taking a bit of extra time. So I pre-calculated which of the industries were actually capitals and stored that in a separate list so that fewer industries needed to be actually looped over. I also pre-calculated a bit more data associated with capitals to avoid some lookups, and this sped things up as well. Seeing how effective my incremental updating of the train references for collision detection was, I realized that a similar approach could be used for updating the train references in the track blocks. Basically, it's the same concept where the track is divided into blocks, and those are used to determine if a block is already reserved and a train can move into it, or if not. And there's a similar concept that you only really need to update these references whenever a train moves into or out of one of those blocks. And that previously I was clearing all of the references at the beginning, and that was taking a significant amount of time, as well as adding it every time was also slow. Now I only need to update when a train actually makes a transition. The final optimization that I made is that it's possible to delay some calculations so that instead of happening every frame, they only happen every once in a while based on the speed of the train. Unfortunately, I was only able to identify one really useful way of doing this, which is that in the game, there's a concept that a train following another train in the same track will not run into it by looking ahead to find what other trains are in front, and if it gets too close, that will stop or slow down to match speeds. This optimization is used specifically for the follow distance calculation and not for inter-train collisions. I had considered doing a similar sort of optimization of putting trains to sleep for the inter-train collisions. Unfortunately, this wasn't really practical because I needed to still do a bunch of lookups for what are the position and the track attributes. And specifically, the track attributes have to be found to know what the acceleration and max speed of the train are for just like the train moving. So there wasn't really much time to be gained, and the train collisions were really fast in the first place after my previous optimizations. I also didn't want to run the risk of making it so that trains would wind up not colliding with each other when they really should, so I left that alone. As a result of all of these optimizations, the total time wound up being 3.54 seconds compared to the 61.68 seconds that it was before, which is a factor of 17.4 times faster. Overall, that was a pretty good speed improvement. It's actually more than I was really expecting from the outset, and this was all doing purely single-threaded optimizations. I wound up doing a fair bit of work in order to get some parallelization also going, but that's a subject for a different video. Thank you for checking out my update.